All right, our last talk of the morning session is going to be a nice mix of algorithms and complexity from Bill Pfefferman.
Okay, thanks. So it's great to be here, and thanks for coming. I know you have a choice. So I'm going to talk about complete characterization of unitary quantum space. Right, so I'm Bill Pfefferman, a postdoc at QUIX in the University of Maryland, and this is joint work with Cedric Lin, who's also a postdoc at QUIX. All right, so let me first tell you my motivation, which is to understand the power of quantum computation with a small number of qubits, okay? And in fact, our results are going to show something far stronger, okay? We're going to give two natural problems that completely characterize the power of quantum computation with any a priori bound on the number of qubits, okay? So the first problem will be the precise succinct Hamiltonian problem. This is a natural generalization of Kitaev's K-local Hamiltonian problem. And the second problem will be a well-conditioned analog of the ubiquitous matrix inversion problem. Okay? So these characterizations have many applications. In fact, our initial motivation for thinking about these issues had nothing to do with space. Okay? Instead, what we were trying to do is answer some particularly basic and foundational questions about QMA proof systems and Hamiltonian complexity. Okay? There are other applications, such as trying to understand the comparative power of preparing PEPS states versus the ground states of general local Hamiltonians, and even to classical log space complexity. Okay, so formally what we're really talking about is quantum space complexity, and the primary complexity class we'll consider is called BQ space K of n, okay? Which is the class of promise problems that can be decided by a bounded error quantum algorithm that acts on K of n qubits. All right, so formally speaking, we'll say that there exists a uniformly generated family of quantum circuits, Qx, each of which acts on at most K of x qubits, okay, with the property that if the answer is yes, the circuit Qx accepts with high probability, say probability greater than 2/3, whereas if the answer is no, then the circuit accepts with probability at most 1/3. This is the BQ, the bounded error quantum part. So notice that nothing really fishy is going on here. If instead of bounding the number of qubits that the circuit is acting on, we had instead decided to bound the size of the circuit, right, by say a polynomial in n, then we would have gotten BQP instead of BQ space. Okay, but we're not interested in time complexity as much as space complexity here, which is simply the number of qubits that each of these circuits acts on. Okay? So our results will show two natural complete problems for the class BQ space K of n, okay, for any k between logarithmic in n and polynomial in n. Okay, and our reductions will use classical K of n space and polynomial time. So I think this is kind of about as strong as we could hope for. Okay? The only subtlety here, the only thing that's not completely standard in all of the space literature, okay, is that we're going to be talking about unitary quantum space, okay, which by definition means we're not going to have any intermediate measurements. We're simply going to apply our unitary quantum circuit, that's Q of x, and we're going to measure some output qubits. Okay, we're not going to worry about intermediate measurements in the computation. Right? So I think this is a little bit odd for people who are used to thinking about time complexity, because we have time-efficient means for deferring intermediate measurements until the end of the computation. Okay? But if you think about how these methods work, they introduce extra ancilla qubits. Okay? So they don't, in general, preserve quantum space complexity. Okay? And it's not known if deferring intermediate measurements can be done space efficiently. Okay, so the way we'll handle that in this talk is we'll just assume that all of the measurements are at the end. But I want to stress that this is not without loss of generality. Okay, so I think one of the most interesting aspects of this talk is that we'll connect quantum space complexity on the one hand with quantum Merlin Arthur protocols on the other. Okay, so what are these protocols? These are problems whose solutions can be verified quantumly given a quantum state as a witness. Okay, so here's Arthur. He's really excited and happy because he has a quantum computer. Okay, and he's receiving a polynomial in n qubit quantum state psi from Merlin, which is supposed to convince him of the validity of some mathematical claim. Okay, so formally, QMA with completeness C and soundness S is the class of promise problems so that if the answer is yes, there exists a polynomial in n qubit quantum state psi that Merlin can send to Arthur, okay, that convinces Arthur, that's V, the verifier, to accept with probability greater than C, the completeness. All right? Whereas if the answer is no, then no matter what quantum state psi Merlin sends to Arthur, Arthur accepts with probability less than S, the soundness. Okay? So if we say QMA with no other parameterization, we're talking about QMA with bounded error, so completeness 2/3, soundness 1/3. Right? And we know from our amplification results that we get the same class as long as the completeness minus soundness, the so-called promise gap, okay, is bounded by an inverse polynomial. Okay, so we'd get the same bounded error class. Okay, so I think one of the main reasons to be interested in QMA is Kitaev's result that says that the K local Hamiltonian problem is QMA complete. Okay, so what is this problem? We're given as input a so-called K local Hamiltonian, which by definition means that the Hamiltonian can be written as a sum of K local terms, each of which, so each of these terms, HI, acts non-trivially on at most K qubits and is the identity on the rest of the space. Okay, and we're just asked, we're promised that either the minimum eigenvalue, okay, of this Hamiltonian, or the so-called ground state energy, is either greater than B or it's less than A, where the gap B minus A is bounded by an inverse polynomial in n. N is the number of qubits that the Hamiltonian acts on. Okay, and we just have to decide which is the case. So you can think of this as estimating the ground state energy to within precision inverse polynomial in n. Okay, this is our standard prototypical QMA complete problem. I think it motivates the study of QMA. Right, but we're also going to be interested in generalizations. So the main one we'll study is so-called precise QMA. So by precise, I mean that the completeness minus soundness gap is going to be bounded by an inverse exponential quantity instead of an inverse polynomial quantity. All right, so the only thing that's really clear about this class, it's completely trivial, is that it clearly contains QMA. Okay, because when the gap gets smaller, you're not going to get less powerful. Okay. Okay, and then a totally generic definition is a K-bounded QMA M, okay, which just means that Arthur's verification circuit acts on K qubits, and Merlin sends an M qubit quantum witness. Okay, so if we just say standard QMA would be the case in which K and M are polynomials, and C and S are 2/3 and 1/3. Okay, great. So let me tell you about this first characterization, which is the precise, succinct Hamiltonian problem. Okay, so this, like I said, is a natural generalization of the local Hamiltonian problem. Okay, so let me tell you about this problem. First, I'll define the notion of succinct encoding. Okay, which is simply, we say that a classical Turing machine, M, is a succinct encoding for a 2 to the k by 2 to the k matrix A. Okay, if on input I, a row index, it spits out the non-zero elements of the ith row. Okay, efficiently, which for us means in polynomial time and using k of n classical space. Okay, so these succinct encodings don't exist for every matrix. For example, if k is a polynomial, and so the dimension of this matrix is 2 to the poly by 2 to the poly, okay, in general, having a succinct encoding will amount to a sparsity condition, okay, that there are at most polynomial number of non-zero elements in each row of the matrix A. Okay. So now let me tell you formally about this K of n precise succinct Hamiltonian problem. We're going to give as input a succinct encoding of a 2 to the k by 2 to the k Hermitian matrix A. And we're going to be promised either that the minimum eigenvalue is either greater than A or less than B. Sorry, greater than B or less than A, excuse me, where the gap B minus A is bounded by an inverse exponential quantity in K of n. Okay, so, and we wanted to know which is the case. So this should look really familiar to us. It's kind of very similar to the local Hamiltonian problem, which I just described, with kind of two differences, which will kind of make all the difference. The first is that the input is succinctly encoded, okay, instead of local. It's kind of a generalization of local. And two, the precision needed to determine the promise is inverse exponential in k instead of inverse polynomial in n. Okay? So that's why, by the way, that's why it's called precise succinct Hamiltonian. Okay? All right, and our main result will be that the K of n precise succinct Hamiltonian problem is complete for this class BQ space K of n. Okay, so let me describe the proof here. The more interesting direction is the upper bound, showing that the K of n precise succinct Hamiltonian problem can be solved in BQ space K of n. For convenience, I'll divide this proof into two parts. In the first part, I'll show that this problem has a precise QMA protocol, okay, in which the completeness minus soundness gap is bounded by an inverse exponential in K of n. Okay, so what we're going to show is a QMA protocol with these parameters, okay? So let's just recall what the problem was from the last slide in case you've already forgotten it. We're given as input a succinct encoding of a 2 to the k by 2 to the k Hermitian matrix A, and we're just asked to estimate the minimum eigenvalue of this matrix A to within precision inverse exponential in k, okay? So here's the QMA protocol. We're going to ask Merlin to send the eigenstate psi that corresponds to the minimum eigenvalue of the matrix A. And now Arthur's going to run phase estimation with one ancilla qubit on the unitary operator e to the minus ia and Merlin state psi. Okay, so here's a picture of the circuit that he applies. It's just phase estimation with one qubit with one ancilla qubit. Okay? And he's simply going to measure this single ancilla, and he's going to accept if he gets 0. Okay? So why does it work? Well, after all, what's really going on here is this phase estimation, okay, with 1 bit of precision. Right? So it's not hard to see that we get the 0 outcome with probability that's just slightly higher, okay, like 2 to the minus k higher, if the minimum eigenvalue of the matrix A is less than little a than if it's greater than b. Okay? But this is exactly what we need to establish the claimed bound. Okay? In other words, precise QMA by definition is a class of problems in which we accept with slightly higher probability in the yes instance, okay, when the minimum eigenvalue is less than a, than in the no instance when the minimum eigenvalue is greater than b. Okay? So despite the fact that this circuit, only does slightly differently, slightly better on the yes instances than on the no instances, this is precisely what we need to get this part of our upper bound, which establishes that this K of n precise succinct Hamiltonian problem is in this kind of precise QMA class. Okay? But of course, the remaining question, which is incredibly important, is how do we implement this operator e to the minus ia? Okay, it's a unitary operator, but we're not given this as input, right? What we're given as input is the succinct, description, the succinct encoding of this matrix A. Okay, so now we don't need to implement this exactly, okay, for this to work, but we do need to implement this operator with extremely high precision. Okay, we need to implement it with precision 2 to the minus k, because otherwise the error in simulation of this operator would completely overwhelm the gap, which is why we're interested in implementing this circuit in the first place. Okay? So luckily, we can invoke recent precise Hamiltonian simulation results of Andrew Childs and collaborators, okay, to show that we can actually implement this operator e to the minus ia to within very high precision efficiently. Okay, so we're very lucky that these exist, and I think these are some of the first kind of applications of these very nice recent precise Hamiltonian simulation results. Okay, so it says that we can implement, these results say that in general we can implement this operator to within precision epsilon in space that scales with log of 1 over epsilon and time polylog in 1 over epsilon. So notice that this is what we want because we're interested in implementing this operator e to the minus ia with precision, inverse exponential in k, and we want the space to be bounded on, by k. Okay, so it's very important that the space especially scales with the log of 1 over epsilon. Okay? See also the talk on Thursday for the latest news on these kind of Hamiltonian simulation results. But anyway, for us, the important thing is using these simulation results, we can implement Arthur's verification circuit in time that scales polynomially in n and in k of n space, which is exactly what we're claiming in the first part of our upper bound. Okay, good. So the second part of the upper bound is a bit more technical, okay? And it's what we're going to show is that this precise QMA class that we just showed in the last slide is contained in BQ space K of n, okay? So this is very much based on the proof, modeled after the proof that QMA is in PP, if you've seen this before. All right, so we're going to start in the same way, which is to error amplify the precise QMA protocol. Okay, so let me tell you the goal, which is to go from a precise QMA protocol that has an inverse exponential in K gap, okay, that is the completeness minus the soundness is inverse exponential in K, to a protocol which has error inverse exponential in K, okay? In other words, the completeness is like 1 minus 2 to the minus K, and the soundness is 2 to the minus K. Okay, so this is the goal. But we want to do this while simultaneously preserving the verification space at K of n. Okay, so I'm not aware of any previous methods which could kind of have these space-preserving features that we need. So we developed these new ideas by combining ideas from in-place amplification of Merritt and Watrous, okay, with kind of clever ideas from phase estimation. Okay, so I want to be very clear. What Merritt-Watrous does is it allows you to amplify a generic QMA protocol in a way that kind of reuses the witness, so it doesn't change this the number of qubits that Merlin sends. Okay, but we need something stronger. We don't only need to be kind of an in-place amplification that doesn't use more witness qubits. We also want to preserve Arthur's verification space. Okay, and so these are the techniques that we develop. All right, so now, if we have this amplified protocol, what we're going to do is simply consider the same amplified verification protocol that guesses the witness, okay? So we're going to consider this protocol run on the maximally mixed state on K of n qubits. Okay, this is going to take a huge hit in the completeness and soundness. They're going to drop considerably. But what's not hard to see is that, as long as our original protocol, our original error amplified protocol had error that was inverse exponential in K of n, we're going to see that this new kind of no witness protocol that simply guesses the witness at random, okay, has a precise gap. So the completeness minus the soundness is bounded by an inverse exponential in K of n. Okay, but now we have a precise protocol with no witness, and we're simply going to amplify again by using these space-efficient QMA error amplification techniques that we used before, okay, that we developed for this purpose. Right, so this is going to allow us to obtain a bounded error, okay? It's going to blow up our time, but the only thing we really care about is the space. So at the end of the day, the space will remain at K of n, which establishes the upper bound, okay? We also use our space amplification, a space-efficient amplification technique to prove hardness. So we show that K of n precise succinct Hamiltonian problem is also BQ space K of n hard. The idea there is we kind of first amplify the circuit, and then it kind of follows from Kitaev's clock construction to effectively build a sparse and therefore succinctly encoded Hamiltonian from the amplified circuit. Okay? All right, so why do we care about this, other than the reasons I mentioned earlier? So it turns out, I think the most important application is to understanding the power of precise QMA. Okay, so we show that precise QMA is exactly equal to PSPACE. Right, so I guess the question we're asking is, how does the power of QMA scale with the completeness minus soundness bound? Okay, so let's recall what precise QMA was. It was the QMA class in which the completeness minus the soundness is inverse exponential. Okay, and it turns out that both upper and lower bounds follow from the result I just showed, the completeness result, okay, together with an older result by Watrous, which shows that BQ P-space is equal to P-space. BQ P-space is just what I was calling BQ space with any polynomial in n space bound. Okay. Right, so I think an important corollary of this application is that if instead of asking, as Kitaev did, to estimate the ground state, how hard is estimating the ground state energy of a local Hamiltonian with an inverse polynomial precision, if instead of that we had asked how hard is estimating the ground state of a local Hamiltonian to within exponential precision, okay, we would actually have gotten a P-space complete problem instead of a QMA complete problem. Okay? So another extension is we can handle this in the perfect completeness case. So in other words, not only do we show that precise QMA is equal to p-space, but precise QMA in which we have perfect completeness and our soundness is 1 minus 2 to the minus poly. This is also equal to p-space. Okay? So a corollary is that checking if a local Hamiltonian has 0 ground state energy is a p-space complete problem. Okay? All right, so where is this power coming from? Why is precise QMA equal to p-space? Okay, so first of all, could the power simply come from the fact that we have a quantum witness? Okay, so could QMA equal precise QMA equal p-space? Could they all equal p-space? The answer is unlikely because QMA is known to be in PP. So if all of these classes are equal, then p-space is equal to PP. Okay. How about precise, how powerful is precise MA, the classical analog of precise QMA? So in other words, could it be that the power just comes from this small gap? Okay, it has nothing to do with quantum computing. Well, it turns out that a crude upper bound on this class, precise MA, okay, is NP to the PP. Okay, and I kind of won't get into it, but we really think that strongly that this does not equal p-space. Okay, it's kind of strictly less powerful than p-space. Okay? So the power of precise QMA seems to come from both the quantum witness and the small gap together, and not from only one of these two things in isolation. Okay? Let me say a little bit more about these precise complexity classes. I think something that's nice about this is we can answer questions in the precise regime about complexity theory that we have no idea how to answer in the bounded error regime. Okay, so for example, how powerful is QMA2? This is this QMA class in which Merlin receives, the tensor product of two quantum states, psi1 tensor psi2. So classically, we really don't know how, if these two things are different, QMA versus QMA2. But in the precise regime, I just showed you that precise QMA is equal to p-space. We can also show from older results that precise QMA2 is equal to nexp. Okay? So in fact, in the precise world, these two classes are probably unequal, okay, unless nexp is equal to p-space. I'm kind of running out of time, but I'll say that we can do something similar with precise QMA, that's a quantum witness with a quantum verifier, versus precise QCMA, which is a quantum verifier with a classical witness. So we can show that likely in the precise world, these two classes are not equal. Okay? We can also show that with perfect completeness, okay, in the precise world, QMA, precise QMA is equal to precise QMA1, whereas in the bounded error world, we have no idea. Okay? All right, let me talk a little bit about matrix inversion. So let me tell you about the classical complexity of matrix inversion. So here's the problem I'm talking about. We're given as input an invertible n by n matrix A with integer entries, and we're promised that either a fixed element of the inverse of A is greater than 2/3 or it's less than 1/3. And we have to decide which is the case. All right, so something that's known about this, it goes back to the mid-70s, where Sankey's algorithm says that it can be solved in classical log squared of n space. Okay? And somewhat mysteriously, we don't believe that this problem can be solved in log n space. Okay, so we kind of have reason to believe that this log squared is kind of necessary and sufficient if we care about classical space complexity. Okay, so in fact, if it's solvable in log n space, then L is equal to NL. Okay, it's kind of the log space equivalent of P equal NP. Okay, so we don't believe that the matrix inversion problem can be solved in classical space, logarithmic in n. Okay? So a natural question is, can we expect to do better quantumly? And a really surprising result, I think, of Tosh MA from 2012 says that, a kind of a conditional answer. It says that if you add a well-conditioned constraint on the matrix, okay, you say you have the same problem that we just talked about, the matrix inversion problem, but you bound the condition number, the ratio of the largest to smallest singular value, by a polynomial in n, okay, then you in fact can solve this matrix inversion problem in BQ space log n in a non-unitary class. So the circuit has intermediate measurements. Okay, but of course this appears to obtain a quadratic speedup in space usage over classical algorithms. But it begs the question, how important is this well-conditioned restriction, right? So in particular, can we use Tosh MA's result as intuition that maybe we should be able to also solve the general, unbounded condition number case in quantum space log of n. Okay? We're going to argue that the answer is no. So here's our results. We're going to show that in fact this well-conditioned matrix inversion problem is complete for actually unitary BQ space log n. Okay? So the first result is that we give a new quantum algorithm for well-conditioned matrix inversion that it avoids intermediate measurements. Okay? So this is a step up from Tosh MA, who needs intermediate measurement in his circuit. Okay? But we don't only prove the algorithm, that's the upper bound, we also prove the lower bound. We show that this is the hardest problem that can be solved in unitary quantum space, logarithmic in n. Okay, so I think this suggests that somehow this well-conditioned constraint, which before was somewhat mysterious, right, is actually necessary for quantum log space algorithms. Okay. All right, so let me just say that we can generalize this from a problem about n by n matrices that uses log n qubits to a complete problem for the class of quantum computation that acts on k of n qubits. So I'll show our third result says that the k of n well-conditioned matrix inversion problem is complete for BQ space k of n. Let me just tell you quickly what this is. We're given as input a 2 to the k by 2 to the k matrix A that has a succinct encoding, okay, just as before, and an upper bound of 2 to the k of n on the condition number. Okay? And it's the same question as before. In other words, is a fixed entry of the inverse of the matrix, okay, greater than 2/3 or less than 1/3? Okay, and we have to decide which is the case. And we can show that this is complete for BQ space k of n. It's the hardest problem that can be solved by a quantum computer that acts on k of n qubits. Okay? So one more result, which I kind of won't say formally, but I think is still surprising. You can read the paper to figure out all the parameters. But so far we haven't been talking about time complexity. We've only been talking about space complexity. Okay, but it turns out by varying the dimension and bound on the condition number, we can use this matrix inversion problem to actually characterize the power of quantum computation with simultaneously bounded time and space. Okay? All right, let me end with some open questions. So can we use this result that I said about precise QMA exactly equaling PSPACE to give a PSPACE upper bound for other complexity classes? So I think what we'd really want is to understand a good upper bound for QMA2. So can we do this by showing that QMA2 is contained in precise QMA, okay, which would show a PSPACE upper bound? Right? How powerful is precise QIP? This is the QIP with inverse exponential completeness-soundness gap, so we don't know. And can we give natural complete problems for non-unitary quantum space? Okay, so we were talking about unitary quantum space. Recall that means that all of the measurements are at the end of the computation. But can we say something interesting about the non-unitary case? Okay, we don't know. All right, thanks.
Any questions for Bill?
Hey, you said something about you had the same upper bound for precise QCMA and precise MA. Do you know the relationship between those two classes at all?
It's a good question. No, I don't. I think the best thing I know at the moment is that they have the same best upper bound. It's a great question to ask what exactly is the relationship other than that, and I really don't know. Yeah.
Okay.
If you consider more precise precisions, like if you go more like double exponential, what would happen? Do you know that, or?
Yeah, it's a good question. So the question, just to repeat, is if you consider like what I'm calling precise, which is like doubly exponential gap. And so for QIP, okay, we know from a result of Watros and collaborators that precise QIP, that is QIP with doubly exponentially small completeness-soundness gap, that's equal to exp, okay? Now, if we ask about QMA, and we ask how powerful is doubly precise QMA, Okay, we don't fully know. We know that it sits somewhere between p-space by our results and exp by the results I just mentioned about QIP. But one thing I can say is that if you have perfect completeness, okay, if your completeness is 1 and your soundness is anything less than 1, okay, then we can show this is also equal to p-space. Okay, but in the non-perfect completeness regime, I don't know.
I have a question. Classically, you never need to run for more than exponential time in your space. Is that true in the quantum case?
Yeah, it is true. It is true in the quantum case, and that's because of the way we define kind of the uniformity condition. Okay. So yes, the answer is yes.
I was confused about that uniformity condition also because the circuits run for less. The classical. It sounds like if I understood correctly that the classical Turing machine that generates the circuits runs for less time than the size of the circuit. So that means that is that right? And so that means that the classical circuit is asked what is the gate at time t and qubit I and just spits that out relatively quickly. Is that right?
Exactly.
Okay. Yeah, behind you. No.
Yes.
What would you say about the relationship between non-unitary and unitary quantum log space? Would you conjecture that they're the same, or whether one is more powerful than the other?
Right. That's a really great question. It's actually kind of the question I was meaning to point out in my last open question, right? Which is that I really don't have a feel for that. So I think what I can say, is that we had one result before we came along that seemed to indicate that maybe there was some power to be gained from intermediate measurements, right? That was Tosh MA's result. We just took care of that result. We said that actually, we can do just as well without the intermediate measurements. Okay, so I think at the moment I don't really have any reason to think that I don't have a particular application in mind that seems to be more powerful with intermediate measurements, but I actually really don't want to conjecture one way or the other. I have no intuition for this, whether or not that should actually, make a difference. That's a good question.
I just want to push Arm's question more. You're saying that somehow you're forcing the circuit to run in exponential time, but so remove this uniform. It's probably there are ways to handle this, right, and allow a long. So, what would you think would what's is there any advantage in running more than exponential time?
Yeah, it's a good question. I mean, so I don't know. This amounts to what happens if you change the uniformity condition, right? The uniformity condition right now says that there's some Turing machine in the background, right? A classical Turing machine that's generating a description of this circuit, right? And at the moment, the way we're defining things, amounts to the fact that there's only so many possible Turing machines that could generate this quantum circuit. Okay, which means that we have a bound on the maximum size of that circuit.
So make it succinct, right?
So if we don't have that, right, and we have a much larger quantum circuit, then I could imagine that you could do more powerful things, obviously.
Hello? Yeah, this is not a question, but I would like to answer that question if that's okay with you, Bill.
Sure.
So that's the reason why we only consider space classes up to polynomial space, because if you only consider space classes that don't use space more than that, then you can assume without loss of generality that the classical Turing machine only uses polynomial time. Above that, we don't really know, but that's the reason why we only consider up to polynomial time, sorry, up to polynomial space, and above that, some of our proofs will break.
Yeah, I guess actually it sounds like the answer is going to be this is an open question, but you could imagine outputting a quantum circuit where you say, here's a sequence of gates, now repeat these x times, where I'm going to print out x in binary, and then, x could be quite large. Actually, I have another question, which is, so you mentioned that the well-conditioned problem is complete, but it still could be equivalent to the ill-conditioned problem, right?
Absolutely, absolutely. I was just, right, so I wasn't saying anything formal about that. It was just, I think it would be reasonable to conjecture that kind of, as the condition number grows, the problem gets harder. But there's no reason, I think there's no real reason in my mind that I feel that way. It could be that there's a collapse somewhere, right?
But to your sort of times, the fact that it corresponds to different time and space, does that give some evidence about it?
Yeah, absolutely. I think, so one way I thought about this when I was coming up with these results is kind of like almost like a space hierarchy theorem, right? That kind of, it gives some evidence that if you give me more space, more qubits, that, somehow you can solve what seems like a more, a more impressive problem. But I don't, like I said, I mean, that's kind of more of an intuition than anything else, because there could be that at a certain point there's a collapse in the kind of condition number hierarchy, right? At a certain point, you can solve a much high, what seems like a harder problem with the ability to solve, a much lower condition number. I don't know how to rule that out.
Okay.
So are there any results to argue for or against if we can postpone the measurements until the end, and do we gain anything for that or not?
Right. So let's see. So I don't want to kind of just repeat things I've already said, but I think this question really, if I'm understanding correctly, it really boils down to, what power do I think we have from unitary versus non-unitary quantum space, right? And we really don't know. So let me give you an example. So suppose we have a QMA protocol. Okay, and we have the verification circuit has intermediate measurements. Okay, and for whatever reason, maybe because I want to preserve space, you don't allow me to defer those measurements. Okay, so we're just stuck with those measurements. Then you can ask, how can I amplify that circuit? Okay, and the best thing we know how to do, okay, is to just repeat several times. Okay, so for example, in-place amplification, the kind of celebrated result, which I talked about of Merlin and Watros, which says that you can kind of amplify without blowing up the number of witness qubits, right? That assumes access to the inverse of the verification circuit. Okay, but notice, right, if we have intermediate measurements, the inverse isn't well defined, right? What does it mean? Okay, so the answer really, is that everything seems to break. We don't really have good ideas for what to do in that case. Now, does that imply that there's somehow more power for the non-unitary case? It's possible. I don't have any examples that seem to suggest that.
If there are no other questions for Bill, then let's thank him again for a nice talk.